In this video, we'll cover Chapter 4 of our managerial book, The Theory of Individual Behavior. I'm going to focus on this from a consumer behavior perspective, but recognize that this could apply to workers, to managers, and other sorts of individuals we might identify. So we'll start with, what is the theory of consumer behavior? The theory of consumer behavior is an explanation of how consumers attempt to maximize utility given their limited budget. When we talk about utility, we're really talking about a measure of the overall happiness or well-being of the consumer by consuming the goods and services they choose to consume. To understand consumer behavior, there's really three sort of steps involved. Number one, define consumer preferences. We have to have a careful understanding of what it is that consumers prefer. Do you prefer more coffee or more tea? Right? We need to understand those consumer preferences. That helps us understand what you would like to buy and what combinations of goods and services would you like to buy. Second, we need to define the limited budget. This means we need to understand the resources that the consumer has available to purchase things with. This is going to determine the opportunity set that the consumer can purchase. 3 is to find the consumer equilibrium. In other words, choose the combination of goods and services that would maximize the consumer's utility, subject to what we have in steps 1 and 2. We're going to boil this down to just looking at two goods as they compare to each other, and in what combination might we buy of those two goods, but understand that this can be extrapolated out to end goods and services available for the consumer. So let's start with consumer preferences and define what we call a market basket or bundle. A market basket or bundle is a set of goods and services that a consumer might buy and the associated quantities of those goods. So for example, a basket we might call basket A could contain 2 pizzas and 5 beers. Basket B might contain 1 pizza and 7 beers. Those are 2 possible baskets that a consumer could buy with their income. To understand the concept of consumer preferences, we need to talk about this concept of being indifferent. This term indifferent in economics is not really any different than we might talk about in non-economic circumstances. Indifferent means that 2 or more baskets that the consumer could choose make them equally happy. So if, for example, the consumer might be indifferent between basket A and basket B as we defined above. You notice a trade-off. Basket B has 1 fewer pizzas than basket A, but it has a couple more beers. That trade-off of pizza for beer might make the consumer equally happy. To study preferences, we need to make several assumptions. The first assumption is that more is preferred to less. This means that the consumer would generally like to have more of the good rather than less of that good. How would we deal with things that are considered bads? Well, we reframe those bads as goods. So for example, we might talk about garbage. Garbage could be one of those goods or services that a consumer might consume. But to reframe that from a bad, like having lots of garbage is not great, right? To reframe that to a good, you would talk about refuse removal, garbage removal. Then garbage removal becomes a good, and more would be better than less. Preferences have to meet this assumption called completeness. Completeness means we can list out all the possible baskets and rank them. So it's possible for us to say the consumer prefers basket A to basket B, or the consumer is indifferent between basket A and basket B. We have to be able to list out all of those baskets and be able to say, does the consumer like this one better than that one, or do they find those baskets to be equally good? The third assumption is transitivity. Transitivity is much like what you learned in algebra. If A is preferred to B and B is preferred to C, then we must assume that basket A is preferred to basket C. That's to say, if the bundle of goods that are in A give us more utility than the bundle of goods in basket B, and B gives us more utility than the bundle of goods in basket C, then A has to be preferred to C. There is a fourth assumption. We'll hit that later on in this discussion. Let's look at an illustration of preferences. So suppose we have 2 goods, food and clothing, and market baskets A, B, D, E, G, and H. A would be 20 units of food, 30 units of clothing. B is 10 and 50. D is 40 and 20. E is 30 and 40, and so on. So I've graphed these points below on a food and clothing axes. So food is on the horizontal, clothing on the vertical. And I've graphed our points here. Point A, we noted, was 20 units of food and 30 units of clothing. Point B was 10 units of food and 50 units of clothing, and so on. I want to start by looking at point G, here in the light blue area. If I'm looking at G, G is 10 units of food and 20 units of clothing. The assumption of more is better means that if I look at G compared to H compared to B, this should make that person happier and happier as they move up that clothing axis. G is less preferred to H is less preferred to B. In other words, they'd prefer to be at basket B rather than be down here at basket G. Similarly, if I look at G to A to E, G has fewer units of food and clothing than A does, so A would be preferred, and E is further out than A. E has 30 units of food and 40 units of clothing, so E would be preferred to A, and A is preferred to G. Similarly, if I compare G to D, more is better. G is less preferred to D. Now I drew a line through B, A, and D just to kind of give a sense of that indifference. This consumer could be indifferent between the points on the line. We actually symbolize indifferent using the tilde sign. So the consumer is indifferent between A and B, and indifferent between B and D, also indifferent between A and D. So we can write it like this. This line that connects those dots is called an indifference curve, or often called a utility curve. The consumer is indifferent between the baskets along that curve, meaning they would be equally happy consuming any of those baskets that are on the curve. They'd be less happy at H and G and more happy at E. I've used this word utility several times now, and I've given it a general meaning, but I want to be able to provide you a more specific definition. This word utility is actually an ordinal measure of the happiness received from consuming a basket of goods and services. You may remember from your statistics class this word ordinal. Ordinal means that it's really just an order, something we can order. So for example, a Likert scale where you'd say 1 is strongly agree, 2 is agree, and so on, we'd call that an ordinal variable. Order matters, but the values themselves don't. So I could call this 1 strongly agree, 2 agree, or I could call this A strongly agree, B agree. I could call this heart, square. It doesn't actually matter. It's just that the order matters. So we're going to apply numbers to our utility often, but really that number could be 10. It could be 10 million. It doesn't really matter. It's just that more is better than less. I've already shown you an indifference curve or utility curve. This is a line that represents the market baskets that would provide the consumer the same amount of utility. An indifference map is a set of indifference curves that represent a consumer's overall preferences. So let's look at what this would look like on an XY plane. The image below is an example of what an indifference map might look like. We have food on the x-axis again, clothing on the y, and we have several utility curves. Assume that we have points along these curves of different combinations of food and clothing that make the consumer equally happy. So the consumer is willing to give up a little bit of food and get more clothing, give up a little bit of food and get lots more clothing, right, along this indifference curve. I've assigned some utilities here just to note that more is better. So we have a utility of 75 at this lower green curve. If we get greater combinations of food and clothing, points that are out beyond the green curve, then we have a higher level of utility. So I've given this blue line a utility of 100 and the orange line a utility of 30. More is better. It should be noted that these numbers are arbitrary. I just put a number on here to indicate 75 is less than 100 is less than 130. The direction of increased happiness is out away from the origin. And this lines up with our initial assumption that more is always better. To move us in the direction of being able to find out the consumer's equilibrium, we need to understand a concept called marginal rate of substitution. The marginal rate of substitution is really the slope of the indifference curve. So if we're thinking about those curves we were looking at in the last slide, it's the slope along the arc of that indifference curve. To define this in words, the marginal rate of substitution is the maximum amount of one good or service a consumer would be willing to give up to get a unit of another and remain equally happy. In other words, to stay on the same indifference curve. This concept of remaining equally happy is important. It means we're staying on that same indifference curve. The equation for the marginal rate of substitution is the negative of the change in the y variable over the change in the x variable. We'll do an example here to help this make sense for you. Suppose Steve consumes only pasta and wine. The following three market baskets are on his indifference curve. Point A, 1 unit of pasta and 8 bottles of wine. Point B, 2 units of pasta and 4 bottles of wine. And point C, 3 units of pasta and 2 bottles of wine. We'd like to understand his willingness to substitute between these points and remain equally happy. This black line that I've drawn between the points is considered his utility curve. And we can just say the utility is 100. At every point along this line, he's equally happy and he gets 100 utils of happiness. Let's start by calculating the marginal rate of substitution between points A and B. So we're talking about the change in point A to B in y over the change in x. Where did we end up in terms of wine? 4. Where did we start out? We started out at 8 units. We ended up with 2 units of pasta, and we started at 1. So where you end up minus where you start over where you end up minus where you start, with the y variable on the top and the x variable on the bottom. We put a negative sign here because this is always going to be a trade-off. So we're always going to get a negative number. And we define this as how many units of the one good you're willing to give up of the other. So we want a positive number of goods. If we do the math on this, on the top, we have minus a minus 4 over 1, or 4. It's important to be able to interpret this, not just to calculate it, right? So what does this mean? This means that the consumer is willing to give up 4 bottles of wine to get that second pound of pasta. It makes a lot of sense that he's willing to give up a lot of wine for that second pound of pasta. If we're looking at this for any given time period, if he can consume 8 bottles of wine and only 1 pound of pasta, 1 pound of pasta is not a lot of food. So he's kind of hungry. He's willing to give up a lot of wine to get a little bit more food. What happens, though, when he goes from points B to point C? So let's calculate the marginal rate of substitution between points B and C. We have minus, he ends up at 2. He started out at 4 bottles of wine. He ended up at 3 pounds of pasta. He started out at 2. So we get minus a minus 2 over 1, or 2. This means that the consumer was willing to give up 2 bottles of wine for that third pound of pasta. So at 2 pounds of pasta, he's sort of feeling pretty comfortable, pretty happy. He's not willing to give up as much wine as he was before because he's got now more pasta in his basket. What we notice as we're moving along this curve, the marginal rate of substitution is going down. This concept of the marginal rate of substitution going down as we move along the indifference curve is pretty common, makes pretty good sense to us as consumers. And this happens when preferences are convex. When we say convex, think about lenses, concave and convex. This is convex to the origin. Remember, concave would be this direction from the origin. I could climb into the cave. This is convex because the cave faces away from the origin. This concept of convexity is the basis of our fourth assumption for consumer preferences. We say preferences are convex, or preferences generally face diminishing marginal rate of substitution. That is to say that the marginal rate of substitution goes down as the quantity of X increases. So just as we saw in our picture above, as the consumer got more and more pasta, they were willing to give up less and less wine in order to get that additional unit of pasta. I want to look at a couple of examples where the convexity assumption doesn't apply, but recognize that these are a little bit more of the edge cases. There are 2 use cases that I want to show you. One is perfect substitutes, and the other is perfect complements. So the concept of substitutes is just like we talked about when we were talking about elasticity. One good could be consumed in place of the other, and complements is when 2 goods are consumed together. For 2 goods to be perfect substitutes, it would mean that we could consume one good in a perfect ratio instead of the other good. So let me give you an example. We could talk about regular and extra strength acetaminophen. Acetaminophen is the generic name for Tylenol. If a consumer considers these two goods perfect substitutes, they could trade regular for extra strength or vice versa in some fixed ratio. So I've placed on the axes regular strength Tylenol and extra strength Tylenol. So for example, a consumer might consume a total of 7 extra strength Tylenols in a given week, or 14 regular strength Tylenols in that same week, or some combination in between. We can see there's a fixed trade-off between extra strength and regular. If they gave up 1 extra strength, they would consume 2 regular. If they gave up 1 more, they would consume 2 more regular strength Tylenol to stay at the same amount of Tylenol. So here we would say they can substitute 2 regular for 1 extra strength. That means our marginal rate of substitution is 0.5. For every half unit of extra strength they give up, they would get 1 regular strength to stay equally happy. Our utility here of 10. If I wanted to draw an indifference map associated to this, I could put in a second line. This would represent for us a second indifference curve for this consumer. And let's say a utility of 17, where they would consume 10 extra strength or 20 regular strength or some combination in between, but still where the slope of that indifference curve is 0.5. Notice when we were looking at the wine and pasta, the slope wasn't fixed. As we moved down that indifference curve, we got different slopes. Well, here we have a fixed trade-off between the two goods, so we have a fixed slope. Now let's look at the example of perfect complements. Perfect complements are two goods that are consumed together in a fixed ratio. Instead of in substitution for one another, they're consumed together. So I've used an example here from my own preferences. When I drink an 8-ounce cup of coffee, I require 2 packets of stevia. I don't really like the bitterness of coffee, so I have to have my stevia in it. But if there's too much stevia in it, it's too sweet and I don't like it. So I've put coffee on the x-axis, stevia on the y-axis, and I graphed that point 8 ounces and 2 packets. At 8 ounces and 2 packets, I get 15 units of utility. If I were to add more coffee to that, I would not get happier. And I'm assuming here that I would not get less happy either, just to make it simple. Again, not a great concept. It means I'm indifferent if I stay along this line, right? Also, 8 ounces of coffee, 2 packets. If I add more packets, I stay at the same level of happiness. Again, doesn't exactly match what I was just saying a moment ago. If I had 16 ounces of coffee, I would have 4 packets of stevia, and I would be at a higher level of utility. More coffee is better than less. And my new indifference curve would be another L-shaped curve out beyond the original one. For each of these pictures of perfect substitutes and perfect complements, we're still looking at that concept of more being better than less as we move away from the origin. Neither perfect substitutes nor perfect complements really hold in most cases, but we could think of a few examples. A perfect complement may occur when we're talking about left gloves and right gloves. I have 2 hands, one is a left hand and one is a right hand. I only want to consume gloves in pairs. Now I want to talk about the utility function, which is really a mathematical representation of that ordinal utility variable. The utility function is a function that assigns utility values to various market baskets a consumer might choose. The example we have here is a straight line equation. I'll show you what this looks like. This says utility is a function of food and clothing are 2 variables here. I put food on the x-axis, clothing on the y-axis, and I've got food plus 2 times clothing is going to give us a numerical value of utility. So let's start by plugging in point A. Point A is 10 units of food and 20 units of clothing. My utility at 10 and 20 is 10 plus 2 times 20, 10 plus 40 or 50. That point of 10 and 20 gives us 50 units of utility. So I have this point A at 10 and 20, and I know that's going to give me 50 units of utility. Let's do the math for points B, C, and D also. So point B is 10 and 30. I get 10 plus 2 times 30, or 70. I know already then, because more is better, that point B is going to be at a higher level of utility, and the math bore that out. Point A is only 50 units of utility, and point B is 70 units of utility. Those would not lie on the same indifference curve. Point C is 30 and 10, so 30 plus 2 times 10, that's 50 units of utility. Notice A and C have the same utility. So when I plot the point 30 and 10, that point C, that's going to be on the same indifference curve as A. So we'll grab our trusty dusty ruler here, and we'll drop in a line. That line represents the indifference curve or utility curve where utility is 50. I know it's a straight line here because I have F plus 2 times C equals some number. So I could rearrange that as F is a function of C or C is a function of F, and it would be a straight line function. Let's go ahead and get the number for D. The utility when we have 30 and 20. So 30 units of food plus 2 times 20 units of clothing. That means I'm going to get 70 units of utility. So that point D has the same utility as my point B, 30 and 20. This is my point D. So again, I could draw a line between those two, and that line is going to represent our utility curve of 70 units of utility. So it's a little different than what we're used to. We choose values of X and Y, or combinations of good X and Y, and we say, okay, which ones of those goods would give us this same indifference curve, the same level of utility? I have a second example for us to look at. Suppose Sally consumes two goods, X and Y. Her utility is given by the function U equals 3 times X times Y squared. I know already by looking at this is going to be convex to the origin. It's going to give us that curvy shape like the wine and pasta graph gave us before. I'm going to do a few calculations by hand to sort of show you how we would graph this, and then I'm going to go over to Excel and show you what I did there. So just for the sake of argument, suppose that the utility is 100,000. I want to take this function and I'm going to rearrange it to where I can find y as a function of x and be able to find several points on that one indifference curve. What I did in that straight line example was I chose 4 points that happened to lie on those two indifference curves. But here I want to be able to say, given a particular utility, what are a few points that are on that line? So I'm going to plug in the 100,000 where the u is and solve for y. I'm going to put y squared on the left. Really, I'm just flipping things across the equal sign. And then I've really got 100,000 divided by 3x. All I did is divide both sides by 3x and then rearrange which side of the equal sign they were on. So y equals the square root of 100,000 divided by 3x. Now I can pick different values of x, plug them in, and I would find points on the y-axis that would give me that same level of utility, 100,000. So let's plug in 10. Say x equals 10, then y is going to equal the square root of 100,000 over 3 times 10, or 30. And if you push some buttons on the calculator, you're going to find this comes out to 57.7. So at 10 units of x, I would have 57.7 units of y, and that would be a point on this 100,000 utility curve. Let's pick another point just for the sake of argument here. X equals 60. I plug that in. Y is the square root of 100,000 over 3 times 60, or the square root of 100,000 divided by 180, right? Do the 100,000 over the 180 first, then take the square root of that jabber, and you get 23.6. So at 60, the consumer would want to buy 23.6 units of Y to stay equally happy. And I would get some kind of curvy guy like this, where the utility is 100,000. I could do the same kind of thing with 300,000, 200,000, pick different values of the utility and plug those in, rearrange, plug in values of X to figure out what the values of Y would need to be for her to stay equally happy. Instead of doing a bunch of that manually, I created an Excel spreadsheet to show us that. So you'll notice I put in here the square root of the value in this cell, B1, divide by 3 times the value in the cell in column A. I've copied this formula down and copied it over. Notice the dollar signs in there. For those of you that are Excel folks, you'll get that pretty quickly. I'm asking it to stick to row B as it copies down for the numerator, and then stick to column A for the value as it moves across for the denominator value there. But that allows us to get lots of values very quickly. And then I created a graph of those indifference curves. So the green line is the one we were drawing manually. At a value of 10, we had 57.7. At a value of 60, we had 23 and some change. And we've got a bunch of other points that would be on that indifference curve or utility curve when the utility is 100,000. When the utility is 200,000, we get a higher number of units of X and Y that we'd have to consume to be that happy, because more is better than less. And so this gives us a small picture of Sally's indifference map between X and Y. We'll come back to Sally later in this discussion when we try to find the consumer's equilibrium. Now let's talk about the second step, the budget constraint. The book defines this as the consumer opportunities or consumer opportunity set. The budget line itself would be spending all of the money that the consumer has on those two goods and services. The consumer opportunity set would be everything on or below that budget line. We can define the budget constraint as a constraint on consumption due to a consumer's limited income. As I mentioned already, the budget line are all the market baskets the consumer could buy if they spent their whole budget. So let us suppose that the consumer's income is $200 per month. They're going to spend all of their income on goods X and Y. The amount of money the consumer spends on X is the price of X times the quantity of X. The amount they spend on Y is the price of Y times the quantity of Y. It looks a little bit like revenue, right? Well, that sort of makes sense. P times Q would be how much revenue the firm gets. P times Q is how much the consumer spends. Well, what the consumer spends is the revenue to the firm. So on that budget line, assuming they're spending their entire income, PX times X plus PY times Y would be spending all of their income on that budget. If I'm looking at this for food and clothing, I could say their income has to equal the price of clothing times the quantity of clothing, plus the price of food times the quantity of food that the consumer buys. I want to be able to graph this and have an equation for this budget line in terms of the sample data we've got here. So let's pretend the income is 200, the price of clothing is 20. This is really $20 per unit of clothing, plus the price of food, $4 per unit of food times the number of units of food. We get our budget line. We could rearrange this budget line, and I'll show you how to do that shortly, but let's go ahead and plot this. Because this is a straight line, as long as I have the two endpoints, I know what the budget line looks like. So I could just calculate the endpoints and get the line in between. The endpoint on the food axis would just be saying we don't spend any money on clothing, we spend all the money on food. So we would take the income and divide by the price of food, and we'd get that endpoint on the food axis, which makes sense. I'm saying I get $200, food costs $4 per unit, I can buy 50 units. If I spend all of my money on food, I can buy 50 units. Well, that totally makes sense. The clothing axis, I would do the same kind of thing. Income over the price of clothing, or 200 divided by 20. If we spent all of our money on clothing, we could buy 10 units of clothing. If we connect those two dots, we will have our budget line. This is our budget line when our income is $200. The budget set is all of this stuff less than or equal to that budget line. We won't really talk about the concept of the budget set because in reality, a consumer would spend their entire budget to maximize their utility. Now, I say that you might think that they're going to be spending all of their money. Some good or service that the consumer might want to consume could be saving. So one of our axes could be current consumption and the other axis could be future consumption. We could be saving some of our money. Remember, we're looking at just two goods, but we could extrapolate this out to n goods. Now, what's the slope of this line? If we look at this, we could go down 1 over 5, down 1 over 5. That slope is important. Remember the concept in the book called the market rate of substitution. The market rate of substitution is how much of one good we would have to give up to get a unit of the other, not how much we would want to give up. Notice one is preferences, what do I want? The other is what does the market require? The market requires for me to get 1 unit of food, I have to give up 1/5 of a unit of clothing. So really, this is the slope of the budget line. And the slope of the budget line is negative price of food over the price of clothing. Whatever the X variable is, that's the price that goes on top. Whatever the Y variable is, that's the price that goes on the bottom. So we get -4/20 or -1/5, which totally matches what we were just saying, right? You'd have to give up 1 unit of clothing to give five units of food, or 1/5 of a unit of clothing to get 1 unit of food. I want to do just a little bit of algebra with this budget line to show you an easy way for us to rearrange this and get a couple of pieces of information out of this. So I want to convert this m equals pxx plus pyy into a y equals mx plus b format. And I'm going to do that initially with our example, but then we'll go back and look at this in generic. So I'm going to write this actually with the units and everything, just because I think it could be illustrative for those of you that are math geeks like me and you like to see things like this. That price of X is really not just it's $4 per unit of F times the number of units of F, plus the price of Y, which was $20 per unit of clothing times the number of units of clothing. We want to get this into a y equals mx plus b form. So I'm going to try to get clothing by itself. To do that, I'm going to start by subtracting out the $4 per unit of F times F so that we get the C term by itself. So I have 200 minus $4 per unit of food times the number of units of food equals $20 per unit of clothing times the number of units of clothing. Now to further get C by itself, because this is $20 per unit times C, I have to divide that across both sides. So $20 per unit of clothing on this side, that will divide out. But if I do it on this side, I have to do it on this side. So $20 per unit of clothing. My 200 right now is actually $200. So I'm going to put that dollar sign on there just so you can see where the units are coming from here. On the right-hand side, I only have C. On the left-hand side, I have $200 divided by $20 per unit of clothing. If I do the math part of this, I get 10. And the units end up being units of clothing. Remember, if I have the fraction on the bottom, I flip and multiply. The dollar signs divide out, and I get 10 units of clothing. Then I have minus, right? The minus doesn't go away. $4 per unit of food over $20 per unit of clothing. That's going to be dollars dividing out, right? And then 4 over 20, which we could simplify, but I want to just keep it like this for now. But the units you would flip and multiply. So this is 4 units of clothing over 20 units of food times the number of units of food. So we get 10 units of C minus 1/5 units of C per unit of F times the number of units of F equals C. Or we could rearrange this, and I'm going to drop the units now. I'll talk about that more in a second. But this is 10 minus 1/5 of F, which totally makes sense. This slope is saying for each 1 unit of F I give up, I get 1/5 of a unit of C. If you're looking at this now and you go back to look at our graph, 10 was that y-intercept, exactly like we learned when we learned about y equals mx plus b. And that ratio of the prices was the slope, negative the price of food over the price of clothing. That is your market rate of substitution. The generic form then of the budget line in y equals mx plus b format is y equals income over the price of y, what the y-intercept would be, how many units of y we would buy if we spent all of our money on y, minus the price of x over the price of y. That gives us our slope times x. Now let's look at how changes affect the budget line. So suppose I talk about income changing. Income started out at $200, and suppose that we have an increase in income. Well, just using our normal consumer brains, we say if we have an increase in income, we can buy more stuff. Our budget set should get bigger. That's exactly what happens. When our income goes up, we can buy more of each good, more of both goods, really, right? That's going to mean a parallel shift in the budget line. It should be noted that we're not talking about the changes in the prices of either of the goods. So there's no rotation of the budget line because relative prices are the same. When I say relative prices are the same, I really mean the slope is the same. That ratio of price of food to the price of clothing hasn't changed. So what does this new budget line look like for us? The new budget line would be somewhere out here further beyond what we had when the income was only $200. And we could find the endpoints for this. So if we said 300 divided by that $20 per price of clothing, we'd get 15 units of clothing. If we spent all of our money on food instead, the price of food hasn't changed, that'd be 75 units of food when the price of food is $4. If income increases, the budget line shifts to the right. We can buy more of both goods. What if instead the price changes? So let's look at a change in the price of food. We started out with our original budget line of $200 when we had the price of clothing was $20. We would consume 10 units. The price of food is $4. We could consume 50 units, or we consume some combination in between those two. If the price of food goes down, let's say $2.50, we're able to afford more goods. Not just more units of food, but we could also afford some more units of clothing, not at that end point, right? Because the price of clothing hasn't changed. But we could afford maybe some point here where we have more food and more clothing than we had before because the price of food has gone down. We could shift some of that money around a little bit. So let's think about what the new food endpoint needs to be. If we have an income of 200 and we divide that by 2.5, we get 80 units of food. Our new budget line then is a rotation of the existing one, making it flatter than it was before. It's flatter because the price of food went down. And remember, our slope is the price of food over the price of clothing. Negative, of course. Negative 2.5 over 20, our new slope is minus 1/8. So when the price of food goes down, that budget line rotates out. What if instead the price of food went up? What would we expect? So if the price of food goes up, we're going to expect a rotation inward of that budget line where you can't buy as much as you did before because food has become more expensive. So our increase in the price of food might look like this yellow line here. And we would have some point of maximum food consumption being something less than 50. If instead the price of food stayed the same, but clothing changed, then we're going to see that budget line rotate on the clothing axis and stay put on the food axis. So let's bring together the concept of preferences and that limited budget and talk about consumer equilibrium, or really what I like to call maximization. The consumer is attempting to maximize their utility subject to their preferences and their limited budget. So the consumer will choose the quantities of each of the two goods to maximize utility subject to the budget constraint. There are two conditions. The first condition is that the basket consumed will be on the budget line. The second condition is that the basket must be the preferred basket, which is to say that that basket must provide them the highest possible utility given that budget constraint. So I've drawn a picture here where we have three indifference curves and a budget line. If we look at points A, B, C, and E, we can afford each of those different points. We could be at A, B, C, they're on the budget line, and E is inside the budget line. We cannot afford D or F, so we know for sure we're not going to pick D or F. If we look at this initial assumption though, the basket consumed will be on the budget line. We're going to use all of our budget. That means we also would not choose E. So we're going to pick a point on the budget line, A, B, or C. Now, I drew this on purpose so that you could see what this would look like with these different indifference curves in here. If I choose A or C, I'm on this indifference curve of 10 utils. I'd be spending all my budget, but I wouldn't be meeting the second criteria of the basket must be preferred. In fact, if I moved in a little bit from point A to some point here, let's call that point X, the consumer would be a little bit happier. More is better. I'd be on a utility curve that's higher than my U equals 10, and I'd be a little bit happier than I was before. I still wouldn't be at the optimal though, because I could move in a little bit further. Let's call this point Y. At point Y, I'm getting a little bit more, and I'm out on a utility curve that'd be a little bit higher than the one that went through X. So the point B is going to be our optimal. Let me summarize. We can afford points A, B, C, and E, but not D and F. E fails the first condition, so we're not considering it. That left us to A, B, and C. B is the optimal because it is the basket that's on the budget line that provides the most utility. So our conclusion here is that the optimal occurs where the budget line and the indifference curve are tangent to each other. That is to say, the lines will have the same slope at that point. So the slope of the indifference curve, which is the marginal rate of substitution, has to equal the slope of the budget line, which is the ratio of the prices. If you're thinking there was a negative in there somewhere, well, remember the slope of the indifference curve was really the negative of the marginal rate of substitution. The slope of the budget line is negative the ratio of the prices. So we can say the marginal rate of substitution has to equal the price of X over the price of Y. In other words, what we're willing to substitute one for the other for in our preferences equals what the market requires us to substitute one for the other for in dollars out in the market. It's possible that we get solutions called corner solutions. These are solutions where the marginal rate of substitution is not going to equal the ratio of the prices. This means the optimal basket will occur at a point where the slope of the indifference curve does not equal the slope of the budget line. These are edge cases, and these are cases where the optimal will always be at the corner or end of the budget line. So I've got a couple of examples for us to play with here. Suppose that somebody likes hamburgers, but is indifferent about soda. I've drawn our budget line in here. Suppose this is an income of $100, and they're going to spend this on soda and hamburgers. We want to think about what the indifference curves or utility curves would look like in this case. The person likes hamburgers, but is indifferent about soda. This would mean that at some amount of hamburgers, the person would get a particular amount of utility. But if they're indifferent about soda, we could give them no soda or lots of soda at that amount of hamburgers, and they would maintain an equal amount of happiness. This then indicates that we have horizontal indifference curves. So let's say this is one hamburger, that gives them a utility of 10. If we gave them 2 hamburgers, they would have a higher level of utility because more is better. They like hamburgers, but they're indifferent about that soda. So more or less soda, they stay at that same level of utility. This might be 15 utils, and so on. So I'm going to just draw on a few more utility curves here. So this might be utility 20. This is a utility of 25. Let's say a utility of, 25, utility of 30. We can't get out to this indifference curve here at the utility of 30. So we know that's not going to happen. But it is part of this person's indifferent map. If they could get there, they would want to get there. They're not going to stop at a utility of 10 because at this point, they're not at the highest amount of satisfaction they could get with this budget. They'd be spending all of their budget, but they'd be buying a bunch of soda, and they're not really interested in soda. They'll drink it if it's there, but it doesn't make them happy. It doesn't make them upset. They're just indifferent. So instead, they'd rather consume more hamburgers and less soda. Still not at the point that they would want to be at, though, right? Not at the highest happiness they can get and achieve full use of the budget. This point here is the place at which the budget line and the indifference curve meet. Let's call this point X, X for our optimal here. This is a corner solution. Notice there's no way that our indifference curves could ever have the same slope as our budget line unless prices changed or something like that, right? And then we'd have to have a very different price structure than what we have in the market. This is a corner solution. We're not going to see the slopes equal each other. More is better is in this direction. The more hamburgers, the better. What if instead the person likes sodas but dislikes hamburgers? When somebody dislikes something, then more of that thing actually makes them less happy than they were before. Now, we said we weren't going to do bads, but I wanted to show you this just so you could get a sense of what this might look like. I want to pick a point out in that XY plane, that soda burgers plane, and start thinking about what an indifference curve would have to look like in this case. It's not going to be straight lines because they dislike hamburgers. They're not indifferent to them. So just for the sake of argument, let's pick a point out here like this. And suppose we want to stay equally happy. If I want to stay equally happy, then I want to think if I move in a particular direction, how do I have to move for the other axis? So let's say I move along the hamburger axis. What would I have to do along the soda axis to stay equally happy? So suppose I'm at this point. I'm going to call it point A. And I said, we're going to give you more hamburgers, but you dislike hamburgers. So to keep you equally happy, what would I have to do? I'd have to give you more soda to keep you equally happy. So some point like this. If I gave you fewer hamburgers, what would I have to do to keep you equally happy? Fewer hamburgers? Well, I'm a little happier now. So you could give me less soda and I could remain equally happy. So these indifference curves may look something like this. And this utility, let's say, could be 10. If I had no hamburgers at all and just this little bit of soda, I would have 10 utils. But the more hamburgers you give me, the more soda you'd have to give me to keep me equally happy. If you think about this, the more its better direction is more soda. So my indifference map is going to be higher utils as I move out in the soda direction. And pretend that those are sort of parallel to each other. And we get something like this. I don't have my trusty dusty ruler here because these have an odd shape. And again, imagination, right? So I've drawn this series of indifference curves that represent this person's preferences where they like soda, but they dislike hamburgers. We can't get out to the utility of 35 because we don't have enough money. We'd end up at this point X as the optimal, where they'd be spending all of their money on soda and they'd achieve 30 units of utility. Notice again, we'd never be able to get the slopes of the budget line to equal the slope of the indifference curve. So we have a corner solution. Let's go back to our Sally example where we had the utility function given by u equals 3 times x times y squared. Suppose the price for x is $10. So this is a new assumption, while the price for y is $5. Sally's current income is $500. We want to determine the XY combination which maximizes Sally's utility given her budget constraint. Remember, we looked at her indifference curves? What we're trying to do is find which combination of X and Y she needs to be at to spend all of her $500 and reach the highest indifference curve she could reach. So I want to start by looking at her budget line. Remember, the budget line is income equals the price of X times the quantity of X, price of Y times the quantity of Y, or in this case, 500 equals 10X plus 5Y. I could rearrange this and get Y by itself. It would be Y equals 100 minus 2 times X. My ratio of the prices is minus 2. That's not a big surprise because I have the price of X is 10. The price of Y is 5, and we know that slope is minus the price of X over the price of Y, or minus 2. My Y-intercept is 100 units, and I could find the intercept for X. Not important, but I just wanted to give you a sense of how that all fits together. My slope, that's the key thing I need out of this equation. I need that slope equals minus 2, or that price ratio is minus 2. That's step 2 from our assumptions. Step 1 would be to get a handle on those preferences, and actually for us, that really means understanding that marginal rate of substitution. Now, this really requires some calculus given that we don't have a straight line indifference curve. So I'm just going to give you the punchline here, and I would not expect you to be able to come up with this on your own. The marginal rate of substitution is 3 times y squared over 6 times xy, or we could simplify this to be y over 2x. Now, you might be saying this is an equation. It is an equation. Why is it an equation? Because the slope is not constant as we move down a curvilinear indifference curve, right? That indifference curve is convex to the origin, so the slope is non-constant. We have an equation for the slope. So from the budget line, I have my slope. From the indifference curves, I have my slope. Now what I need to do to find the optimal is set the budget line's slope equal to the marginal rate of substitution. Now remember, I'm going to do those in absolute value. So set the marginal rate of substitution equal to the ratio of the prices. So set the marginal rate of substitution equal to the ratio of the prices. I get y over 2x equals 2, right? The slope in absolute value, or the ratio of the prices. Well, let's write it out. So y over 2x, 10 over 5, or 2. And I'm just going to rearrange this and solve for y. Since 10 over 5 is 2, and then I take 2x and I multiply it by both sides, it drops off of the left, so I get y equals 2 times 2x, or 4x. This guy is now an important equation for us. This actually tells us what the relationship is between x and y at the optimal. So that means there's some line y equals 4x where our optimal is going to be on that line. That's the relationship between the x and y at the optimal. So if I have 1x, I have 4y. If I have 10x, I have 40y. That's what that means. So now I have two equations, two unknowns. I have my relationship between x and y at the optimal, and I have the budget line. So I'm going to put my budget line down here. That's one of my equations. The other equation is y equals 4x. I'm going to actually basically set these two equal for each other, or substitute in the 4x where the y is here. 4x equals 100 minus 2x. So I've got adding the 2x across, 6x equals 100, or x equals 16.7. At the optimal point, the place where the budget line and the indifference curve meet, this person, Sally, would consume 16.7 units of x to be at the optimal. That gives us that optimal number of units of x, but we still need to find y. So to find y, we're going to plug that x optimal value into one of the two equations. It doesn't matter if we use the budget line equation or if we use the relationship between x and y at that optimal equation. Two equations, two unknowns. You could use both. That would give you a nice double check that you actually did find the point of intersection. I'm going to pick the one where it's y equals 4 times x because it's less math for me to do. So y equals 4 times x, which is really y equals 4 times 16.7, which gives us 66.7. So at the optimal, she's going to consume 16.7x and 66.7y. We know how many units then she's going to consume. There is one additional question that we might want to ask. This is a little bit more optional. This would be, what is her level of utility at the optimal? In other words, how many utils is she getting out of this basket? Remember, utils is an ordinal measure, so it's not super useful in and of itself. It would only be useful when you're comparing one point to another point, but we could calculate it nonetheless. So remember, the utility function is 3 times x times y squared. So if I plug in what we know, we have 3 times 16.7 times 66.7 squared. And if we simplify that, we get 223,558 utils. So not on any of those indifference curves I drew before, but we would get that level of utility at that point, and we'd know that this is somewhere between those other indifference curves we were looking at. There's one last concept I want to cover in this video, and that's because it was a bit more complex for me to understand as a student, so I wanted to make sure I spent a little bit of time talking about that. And that's looking at the substitution and income effects of a price change. That sounds like, well, what are you talking about, right? What's going on here? Well, so we looked at those price changes before, and remember, it caused a rotation of the curve. What this is actually doing is breaking down that rotation of the curve and the impact that that has on the optimal quantity that would be consumed. It breaks that change down from point A to point B into two pieces, an income effect and a substitution effect. So we want to break down that rotation of that price change and the impact that that has on the optimal quantity that would be selected. When the book discussed this, they did an example of an increase in price for a normal good. So for my example, we're going to do a decrease in the price for a normal good. I think showing you the other direction will help you put the pieces together better, especially if you've actually read the book. What we want to do is see the impact that that price change has on the optimal basket that the consumer will choose to consume, divided down into two pieces. So again, assuming this is a normal good and that our price is going down, we're going to look at these two pieces. The first piece is the substitution effect. The idea of the substitution effect is when that price changes, the price of the one good changes, the price of the other good's not changing, we'll substitute away from the more expensive good towards the less expensive good, whichever one that is, whether it's the price of the good that's changing or the price of the other good. So we want to break down what that substitution effect looks like. To do that, we're going to rotate the budget line to the new slope, the new ratio of those prices, but keep it on the same indifference curve. So suppose the ratio of the prices, once price of X goes down, is something flatter like the slope I've given by my ruler here. So we'd get a budget line for this substitution effect that would look like my dotted line here. I'm drawing it in as a dotted line because in reality, this is not our budget line. This is saying what happens when the price ratio changes and I'm staying at the same level of utility. So I look at where that new budget line or that new sort of imaginary budget line hits the utility curve. And I say, okay, if this was actually the budget line, what would they consume? They would consume this X2 units of the good. This change between X1 and X2 is the substitution effect. How much would we substitute away from Y towards X if the price of X goes down? The second piece of this is the income effect. For the income effect, what we're going to do is rotate the budget line out to where it would actually be and find the new optimal place. Then we'll determine how much more X changes from X2. It could shift forward or back depending on whether this is a normal good or an inferior good. So let's take our original budget line and rotate it out to where the new budget line would be. That new budget line would look something like this because that price of X has gotten cheaper, and I've gone way off the map there, but you'll get the point. And our new indifference curve is going to be just tangent to this at some point, so let's draw that in. Suppose that this now is our new utility curve. I know it doesn't look exactly like the other one, but pretend with me here, and we get a new optimal point where the new budget line touches the new indifference curve that we're able to reach because the price has gone down. This change from X2 to our new higher amount of X3 is the income effect. The total change from X1 to X3 is because we've decreased the price of the good. Part of that is substituting away from Y towards X because X has become relatively less expensive. And part of that is we can buy more of both because we've got more relative income anyway, right? Income itself hasn't increased, but relative to that price, we have more purchasing power, really. That new optimal point here we'll call Q actually has us consuming a lot more of X because X has become relatively cheaper and about the same amount or maybe slightly less Y. A final concept to look at is the derivation of demand from these budget lines and indifference curves. And I've already sort of mapped this out a little bit so we can look at it fairly quickly. But I wanted to show you how we get that law of demand and derive the demand curve from these points that we've already talked about, these optimal points in the consumer's consumption bundles. So I've got the price of X being $15. That's represented by the blue lines. So if the price was $15, she would have this rotated in, very small looking budget, and her optimal would be point A. At a price of 15, her quantity then would be here at 5. This would be point A. If the price were to go down to $10, that price of $10 means a rotation out of that budget line, just like we were showing up above. She would be able to reach a higher indifference curve, and on that higher indifference curve, she would consume a greater number of units of X. So I've said, hey, at a price of $10, she consumes 10 units of the good. And again, I'm just making up numbers, so it doesn't exactly make sense, but just to give you an idea. At a price of $5, her budget actually is able to buy lots and lots more, even though the income hasn't changed. She reaches an even higher indifference curve, and at point C here, she gets 17 units of the good. I wanted to note primarily that at every point along this demand curve is an optimal point for the consumer. At point A, she is as happy as she can possibly be given that price of $15 and her given budget. Given the price of $10 and the current budget at point B, she's as happy as she can possibly be. Each point on the demand curve is an optimal point for the consumer. Be sure to read the examples in the book about workers and managers. Those are really useful to help you understand additional applications of this individual behavior theory. Thanks for watching.